I'm Aaron Wagner from Electrical Engineering, and it's my pleasure to host and welcome Jayadev Acharya, this week's speaker, also from Electrical Engineering. So downstairs, third floor. So Jayadev, educated at IIT Kharagpur, UC San Diego, postdoc at MIT, and has worked for a number of years now on problems of estimating properties of distributions from samples. Not really the whole distribution, but finding how you can use fewer samples to learn things like entropy and other things you care about are probably distributions. He's won various awards for this work, including the ISAT, IEEE International Symposium Information Theory Student Paper Award, an ICML Honorable Mention Paper Award last year, 2017, I think. Okay. Anyway, so recently he's been looking at variations in these problems where the information is distributed and you have communication constraints, and has obtained some very interesting results that I've heard sort of in piecemeal form on my chalkboards, and Jayadev has just figured it down for me. Looking forward to hearing kind of the bigger picture. So, welcome, Jayadev.
Thanks, Aaron, for the kind introduction. I'll try to speak a little, not try, I'm bound to speak a little slower today for the throat. So bear with me if we derail at some point, we might have to stop and get time to think about what we are talking about. Okay, so this is statistical inference under local information constraints. This is a joint work with Clement and all at Stanford and Himanshu at Indian Institute of Science. And this is a brief outline of the talk. We'll motivate and give some methods, then talk about proofs and some of the future directions. Okay. Let's look at the setting. It's extremely simple. We have a so P denotes a discrete distribution over K elements. So K is the set 1 through K, and P is a discrete distribution on this. What's the distribution? It's a map from, it's a function from 1 through K to 0, 1, such that they add up to 1. So probability of 1 to probability of K is 1. So for example, if you have a dice, then K is 6, and P of 1 plus P of 2 and so on up to P of 6 will have to be 1, because every time you roll, you have to see one of these numbers. Okay? What are the kind of questions we are interested in? So throughout this talk, let I denote some task that you want to perform on this unknown distribution P. For example, you may want to estimate what the distribution is, or you may want to estimate its entropy. So H of P is called as the entropy of P, which will not define throughout this talk. So if you don't know what entropy is, it's okay. Or we may ask, is P the uniform distribution? So you can denote the uniform distribution, which means that, for example, the die is fair. We may ask questions like, is P the uniform distribution? And how are we going to solve this inference task? In a standard setting, we are given independent draws. So x1, x2, and so on are independent draws from this unknown distribution P. And upon observing these draws, our goal is to solve whatever inference task we are given. So for example, you have a die and you keep rolling it again and again, and you roll it 100 times. Looking at that, you may be interested in knowing what's the probability of seeing a 6. Okay? Any questions about the setting? Okay. And there is one definition, which is the sample complexity, which is defined as the smallest number of draws that we have to get from P to solve the problem I. So the inference task I has all the parameters inside of it. So once we know what is the task, we want to characterize what's the smallest number n for which we can solve I. Okay? That's the goal. So we want to have the least number of draws from this distribution to answer whatever question you are interested in.
So when you say estimate P, you put an error bound?
Yes, we'll talk about it very soon. So in this talk, we'll consider the following distributed setting. The draws that we set x1, x2 up to xn, they are distributed across n players that are far away from each other. So x1 is with the first player, x2 is with the second player, and so on. Xn is with the nth player. And each of these players can now send messages to a referee R. And the player I sends a message mi. So the player I has a sample xi from the distribution P, and it wants to send a message m of I to the referee R. And the centralized referee now wants to solve the problem I. So there is a distributed setting where the data is distributed, and the centralized referee wants to solve whatever inference task we are interested in. So this is what I said before, the data is distributed over n players, and the player I receives exactly one raw x of I, and then it sends a message m of I to R. And as I said, looking at these messages m1 to mn, now the referee wants to solve the task I. Okay? Now, what are the limitations, or what is the regime in which we are going to study this problem? So if we do not have any constraints, then each player can just send the message to be the sample that it sees. So if you roll a dice and you see a 4, then you will just transmit 4 encoded at some bits. Okay? So this will reduce to the classical setting where you can just aggregate all the samples at the central referee and solve the problem. Okay? So that's not super interesting. We look at two applications or two regimes of interest. One is the communication starved messaging, where you'll assume that each message m of I is at most L bits long, and L is less than log of k. So k is recall that k is the domain size of the distribution, so the distribution is over 1 through k. So if you have log k bits, you can send the sample without any problem. So we are going to assume that L is less than log of k. And throughout this talk, it's easiest to just assume that L is 1 bit. Each person can send just 1 bit, let's say, and we'll see what happens in that. Okay? And another case that we'll touch upon at the very end is differentially private messages, where each message mi should not reveal a lot about what the sample is. So inherently, you cannot send the whole message. You have to add some kind of noise and then send this message over. So we'll spend most of the talk on this communication starved regime. Any questions about this?
So you creating a protocol?
We'll talk about that in the next slide. Thank you. Yeah. Okay, so what does it mean with messaging? We are going to focus throughout this talk on simultaneous message passing. What does it mean? All the messages are sent by all the players simultaneously. So in other words, player 1 sends and player 2 is not able to see what the messages are. The other setting is also equally interesting and perhaps even more challenging. So that's maybe for future sometime. So all the messages are sent simultaneously. However, we are going to consider both the role of private randomness and public randomness. I'm going to spend a few minutes on this in case people are not familiar with it. So we'll consider both private coin and public coin protocols. So what are private coin protocols? Beforehand, we know exactly what each player is going to do, and each player, so the player I is going to see x of I, and then it's going to transmit a random message mi, which is just a function of xi. Maybe a randomized function of xi, but it just depends on x of I. Okay, so the player rolls a die, sees a 4, and then outputs a distribution or a distribution over messages that depends only on 4. Okay? So in other words, the message mi is a randomized function of only the sample at player I. Okay? And this is different from public coin protocols, where there is a random bit or there's a random string that can be generated by the referee. That's why, and then what the referee does is to transmit it to all the players. So now all these players have this common source of randomness u. Or you can just think, that's why it's called public coin. There are public randomness that's available to everyone. Maybe there is a big board somewhere and random digits are being generated over there and everyone can see it. Okay? So this in some sense is a synchronization between the players. Okay? I can give random bits that's shared between the players. And now m of I, the message that player I sends, will be a function of xi, the draw that it sees, the sample at player I, and u. Okay? and the public randomness. Yes?
Does the player have to use all the bits that were generated, or can they choose a subset of them?
That's great. So right now we are going to assume that U is an infinitely long string, let's say, or it's a very long string, each player can do what they want. But we know what they are going to do. Like the referee knows what U is, and the referee knows what these people are going to do. Yes?
Is the protocol public, which every exercise can use?
At least the referee knows. Other players cannot. So it's like pair work.
What's the difference between private coin and thing? I
So-
think both are equivalent. Can you give an example of it?
An example is this. So we'll actually come to an example where you'll see a big gap. Otherwise, I'll describe. So let's say you have two different schemes you can use. He has two different schemes he can use. Now I'm going to tell you when you use one, he has to use two. When he uses two, you have to use one. That I can do by sending random bits. Okay, that's how I can synchronize with public coins. All right? Yeah.
What is a case when you have some maybe not random protocols? For example, if you have only one player and two players, so would I just tell the player one to use protocol one and the player two to use protocol two? Is that allowed or?
Yes, it is by the public coins. Yeah.
Okay, but here there is no need to have a random thing. There is only public things here.
So you can be random, you may not be random.
Okay, I see.
So, but if you, let me just restate it actually. If you are going to say a fixed thing, you can encode it beforehand, that will actually be just private coins.
Okay.
If I'm going to deterministically tell him, then I might as well have told him before anything starts.
Oh, I see.
Okay? Let's see, any other questions about this? Okay, great. And one of the questions that we'll study is, do public coins actually help in some nice looking simple task? Can we show a gap or can we show a clear help that public coins can give? Okay. So we'll, as was one of the questions, we are going to look at the estimation or testing, and for these kind of problems we have to define some distance notion between distributions. And throughout this talk we are going to only look at the L1 distance between two distributions. It's also twice the statistical distance or the total variation distance. And it's just defined as the L1 norm of the difference of the two distribution vectors. Okay? And one thing to keep in mind is if the distance is small, then if I give you a draw, you cannot tell which distribution the data came from. Okay? For example, if L1 of PQ is 0, then the distributions are identical. If I give you a draw, you won't know which one it is. Okay? Again, yeah, it's one of the most commonly used, so that's why I'm going to use it. What are the questions that we'll study in this talk? The first is going to be denoted by IL, L for learning, and K will denote the domain size and epsilon will denote the accuracy. And the problem is the following. Upon observing these draws x1 through xn, our goal is to output some p hat such that with some high probability, where it's just 0.9, the L1 distance between p and p hat is small, is less than epsilon. Okay, so epsilon is some parameter that's given to you. Now you make many draws, and your goal is to just, as you keep seeing more and more draws from the distribution, you will get a better and better estimate, and this is the goal. The other goal that, the other inference task that we'll look at is called uniformity testing, or you can also call it as a hypothesis testing problem, where the goal is the following. We are again given draws from this distribution, and we have to decide, is P equal to the uniform distribution over K elements, or it's a distribution at L1 distance at least epsilon away from uniform. So it's a clearly defined, well-defined problem. All right. Any questions about the two questions we are studying? Okay. All right. So this is what we know about the two problems. For the first one, when you want to learn a distribution over K elements up to accuracy epsilon, the number of draws that we need is K divided by epsilon square. So if you want to estimate a distribution over K elements, you need linear in K observations. and the dependence on epsilon is inverse epsilon square. Okay, so for learning, it's linear in k. That's all we need to remember. For the testing problem, the sample complexity is square root k over epsilon square. I've given a reference here, but we'll come to a little later.
Are you
Yes.
taking that from the Chebyshev inequalities? Like those bounds that the rates at which you're going out? The epsilon.
The epsilon?
Square. The
Yeah.
square, the rate. Where do you take it from? What inequality are you using?
So for the first problem, for example, you can show that the L1 squared rate goes as 1 over n with the number of data points. So the L1 norm will go as L1 distance will go down as 1 over square root n, and you equate that to epsilon. So 1 over square root n will be equated to epsilon, so you get n equal to 1 over epsilon square. Okay. And something slightly similar happens here, not exactly, but very similar. Okay, so the two problems, one is much easier than the other. Testing you can do with square root k samples. It's almost like the birthday paradox. With square root k, you are able to see some kind of collisions, and you can use that to test for uniform. Okay. All right. So now we are going to study these two problems in the extremely communication starved regime, where our x1 through xn are over these players, and each of them can now send just L bits where L is less than log of k, like 1 bit. And the question is, how does everything change? Okay. So before we do that, so this is how actually, perhaps this entire talk may be exactly the order in which we looked at the problem and we solved things. So this is the first thing we thought. Let's see if we can. So this is the question that we came up with. So suppose the referee can actually solve this problem. The referee can look at these messages, and the referee can generate a sample from the distribution by looking at the messages. Okay? That's the task. That's a very simple question that we are asking. So each of these messages are L bits long, and the goal of the referee is to generate one pure sample from P, from the true distribution. Okay? So the referee doesn't have access to P, it only has access to the messages that were sent from the people who have the samples. So for example, if we had log k bits of communication, the first player can just send log k bits and we are done by communication from just one player. So the question here is, you have this centralized referee, can it simulate one sample or one draw from the distribution P after looking these messages that are not long enough to describe? Okay, and yeah, so that's the goal. And the observation is that if we can do it, then hypothetically we can solve any kind of inference task that can be solved in a centralized setting, perhaps with a blow up in number of players or number of samples, but we can solve it. How? Use a bunch of players, simulate one sample. Now keep doing it until you have enough samples to solve the problem in the centralized setting. Okay? So that's it, that's the question. So here is, this is actually not that surprising.
Being able to see. So you're saying it's economic. If you can learn the distribution, therefore, it's not obvious you can get some.
No, if you can simulate, then you can solve. It's not clear the other way is correct.
So then proving impossibility of simulation doesn't say anything about.
Does not say anything. That's completely correct. But it was still interesting to us. Yeah.
And this may not be the most efficient, right? Because with
That's what we are going to consider in this whole talk. That's a great question. Yeah. Okay. All right. So we'll first take an impossibility. This is like playing. So with L less than log k bits, there is no distributed simulation algorithm that will work with a finite number of players. Okay. So there is no algorithm to simulate that has, in the worst case, finite number of players. So almost like how these questions are there, right? Generate fair coin from biased coins, or generate things like that. So this is in that flavor. Not exactly the same, but this is one question you can think. And the proof is actually it's again I'm just writing one keyword. There is a lot of more things that go into it. So each player is now able to send less than log k bits. So it's going to get confused with two messages that two possible inputs. So up to 1 through k, there are two of them which have a positive probability of being mapped to the same message. And you use that to get some kind of contradiction even when you have many players. Yeah?
Can this be used for uniformity testing? Because, for example, if I have uniform distribution over n bits, I can assume the independently bitwise, and I can assume each one of them is sending just one bit, right? So, if I just take, let's say, first bit from first player, second bit from second player, and so on, and construct a sample.
Yeah,
and,
that won't
if-
work. So if you take, wait.
If the original distribution was uniform, the sample.
If you
would
know
be
that the
uniform.
original distribution is uniform, the central referee can do.
Yeah, so this
We don't need
is
anything.
for uniformity testing, correct? First math problem. So you decide the two problems in
Mhm.
uniformity testing.
Yeah.
So,
Maybe we can.
sure.
I'll bother you.
Yeah.
And, or maybe we'll come back to that.
Yeah.
Hopefully. Okay. So again, this will lead to some kind of contradiction. Okay. So again, this is a nice exercise to think about. Another. So that was impossibility. We'll show some kind of possibility. So there is a private coin algorithm. So there is a protocol such that with expected number of players. So this is an algorithm that may never terminate. They're called like Las Vegas algorithms. Algorithms that may not terminate, but when they terminate, they will give you a pure sample from P. Okay? So there is a distributed algorithm with expected number of players as k divided by 2 to the power l or 1. So this is just or max of the two. So if l is 1, then with k players, I can simulate one pure sample, which requires just log k bits to represent it. Okay? And this is optimal, even if you allow public coins.
Can you get this if you do like fundamental extractor on each bit?
Essentially, we are doing some kind of trick like that. So the proof, actually, upper bound, I've left it as an exercise. It's I can tell you the high level thing. So what the first player does is to send an indicator of 1, of whether the sample is equal to 1. Second player does indicator of 2 and so on. Actually the first two will do indicator of 1 and then you build some kind of algorithm on top of it and you get it. But it's actually optimal. In other words, there is no algorithm that takes fewer than these many players and is able to generate a pure sample for any. Okay, the lower bounds follow from a bunch of works on distribution learning, because if you could simulate with fewer than these many players, then you can solve all the inference tasks with something that's lower than the well-established lower bounds. Okay, that's what we'll see. Alright, so now let's look at the two tasks we were looking at. So this, suppose I is any centralized task with sample complexity S. Then what we are saying is there is a private coin algorithm to solve the same inference task by using S times k divided by 2 to the L players. Why? By using k divided by 2 to the L players, we are able to simulate one pure sample, and after we are able to simulate S samples, we are done. Okay. Any questions about this? Yes. What happened to the max? So L is assumed to be less than log k. If L is more than log k, it's just S. Every player just sends their sample. Yes.
If you had ability to, instead of have exactly, like generate exactly from that distribution, but if you can generate from like almost that distribution,
Yes.
would you be able to, would that just translate into some?
That's a great question, and I think from the lower bounds, we can show that you can't even do that,
Oh, you can't even do
because that
that.
will imply a contradiction for the lower bounds of this learning tasks. All right. Any questions about this? Okay. So, this suddenly becomes too Easy, right? So okay, let's look at this table because we'll try to fill in this table better and better as we keep going. So we'll consider only two tasks, as I said. One is learning, one is testing for uniform distribution. These are the sample complexities that we described in the centralized setting, k over epsilon square and square root k over epsilon square. Now suppose we consider the distributed setting with n bits of communication from player. We have right now designed, by using these simulation protocols, we have designed algorithms whose sample complexity is k over epsilon square times k over 2 to the n. And similarly for testing, root k over epsilon square times k over 2 to the n. And again, as I said, so easiest to remember these things is just for one bit. The complexity of learning becomes from k over epsilon square to k square over epsilon square. Testing from root k over epsilon square goes to k to the power 3 over 2 over epsilon square. Okay? We keep having this table again and again, so it will reinforce. Okay? So one bit, everything blows up by a factor of k. Are these optimal? So that's what we will look at. Is the simulate and infer scheme optimal? Can we do something better? Yes, so for learning, this paper showed that the optimal sample complexity is k square over 2 to the L times epsilon square, even with public randomness. Okay, and we have a separate proof of this thing, but so those guys, they came up with a scheme that they are able to show lower bounds for schemes that work in different rounds, like not simultaneous message passing. We have a different optimal algorithm which is simulate and infer. So right now we just showed another way of getting this upper bound, k square over 2 to the L epsilon square for learning. Okay. So for learning, this scheme is optimal even with and without public randomness. Okay, so we just showed an upper bound that uses only private randomness because you can simulate the samples with private randomness, and the lower bounds hold even for public randomness. So private randomness, public randomness, both have this optimal. So now for testing, we just showed this, which is root k over epsilon square times k over 2 to the n, which for n equal to 1 becomes k to the power 3 over 2 over epsilon square. The question is this optimal or not? And what we'll show is, for the testing problem, we can get better bounds by using public coin protocols. And then we are going to show that the simulate and infer algorithm is optimal if we do not have public coins. Those are the two things we are going to show in the remainder. Okay? So let's see. There is a public coin algorithm. So now we are given shared randomness between these players that can solve the same problem with a blow up of, instead of k divided by 2 to the power n, square root of k divided by 2 to the n. Okay, so when L is 1, this requires k over epsilon square samples instead of k to the power 3 over 2 over epsilon square. Okay. The proof, this one I think we'll try to prove. Okay. Yes?
Right. Is it better?
I've written theta here. We are going to look at lower bounds in a little bit. Yes, this is right. Okay. So here is the scheme. This is the second scheme we came up with. The first one was more complicated. For one bit, here is a very simple algorithm. The referee is going to generate a random set of size, random subset of k of size exactly k over 2. That's the public randomness. Okay? So the goal of all of these players is to decide whether P is the uniform distribution or far from uniform. The referee is going to tell everyone, or is going to make everyone agree on a random subset of size exactly k over 2. Okay? And the player I is going to send the message which just indicates whether its sample is in this random set or not. Okay? So player I sends message mi, which is the indicator of xi, the sample present at player I, indicator of xi in S. S. Okay? Any questions about this?
That's uniformly random.
The S is uniformly random. Yeah. So it's one of the k choose k over 2. Okay. So what happens when p is actually the uniform distribution? Then what is the probability that message I is 1? So probability that message I is 1 is the probability that xi, the drop, is in the set S. The size of set S is exactly half the domain size. If the distribution is uniform, the probability of seeing something in half of this domain is exactly 1/2. Okay? Any questions about this? So if the distribution is uniform, the message S will look Bernoulli half. Now if the distribution is not uniform, so let's say P is more than epsilon away from the uniform distribution, then you have to prove this. Then with some positive probability, at least 0.1, when you pick a random subset, so this probability is over the randomness in S, because S is being picked uniformly at random. When you pick a random subset, the probability that it's a little away from half is at least 0.1. So with probability at least 0.1, the probability of a random subset of size k over 2, according from the distribution P, is away from half. Does this statement make sense? What we are saying is, if a distribution is not uniform, you pick a random subset of size k over 2. The probability of this subset according to uniform distribution is exactly 1/2, half the domain. But if the distribution is not uniform, then this will also be away from a half with some reasonable probability. That's all we are saying. Okay? The proof of this again one statement that you can go back and prove and you use this called Cayley-Zygmunt inequality, which I was telling you, and it's an extremely nice inequality to prove that things do not concentrate, that things are far away from where you expect them to be. So for example here, the expected value of P of S is exactly a half. So you take expected value of P of S for all sets of size k over 2, that will be 1/2. However, this thing doesn't concentrate too much around 1/2. It has some spread, and we prove that it has a good spread with. Okay. So that's what we prove. So for the second case, here is one question that we are going to need to solve. If I give you tosses from a coin, and I ask you to decide whether it's a fair coin, meaning its probability is 1/2 for heads and 1/2 for tails, or it has a bias of at least delta, namely its probability of heads is at least 1/2 plus delta, or at most 1/2 minus delta. So it's not very close to 1/2, so it's biased by at least delta away from 1/2. Then this problem has an optimal complexity of 1 over delta square. So with 1 over delta square tosses, you can decide whether a coin is 1/2 or delta away from 1/2. Now we are going to use delta to be omega over, delta to be epsilon over root k. What we showed is now messages coming from these individual players are at least epsilon over root k away from being fair. Okay? They're at least 1/2 plus epsilon over 2 root k, or at most 1/2 minus epsilon over 2 root k. Once that happens, now we can distinguish between the distribution being uniform, which corresponds to message being fair, with the other case with 1 over, so this is the delta, so 1 over delta square will be k over epsilon square. Okay, so with single bit public coins, k over epsilon square players suffice, which is better than k to the 3 over 2 over epsilon square when you did not have public randomness. Any questions about this?
Is the only use of public randomness that you can implement an adaptive protocol?
It's not adaptive, they can just synchronize.
Okay, to state it differently, if I had an adaptive protocol, this would have fallen. So in some sense, you can simulate adaptive protocols using public randomness. Is that fair? Or?
If you had adaptive protocols, you can simulate public coins. I'm not sure. Any kind of.
Because I could generate the coin myself. And
You'll just send the coins. Okay, that's yeah.
So I'm really confused. So are you saying that the test is the same across all the players? So you're going to
Each player gets one sample.
Right, but like in the previous thing, you selected this two subsets that.
So I send one subset to a bunch of players, to a lot of players.
But is all players have the same subset or?
Uh,
Because
That's a great question. Actually, it's about this point
because what
one.
I'm thinking is the following. Suppose that all the probabilities are the same and two probabilities are different. If these two probabilities end up being in different subsets, then I'm not going to say the difference, but
That's
it's
a-
not a fair.
That's a great question. And that's why we have this probability of 0.1. You have to repeat with different subsets at least 10 times for this algorithm to work. So with probability at least 0.1, P of S will work for you. So you just divide the whole set of players into 10 parts and repeat it with a different subset on each of them, then it will work. That's a very good question. I wanted to slip it on the other. Thank you. Alright, so this is the current table that we have. We have said that for learning, the optimal sample complexity is this. Simulate and infer is optimal. For testing, we have this root k in the centralized setting. We have private coins with k over 2 to the L blow up. We have public coins with only a square root of k over 2 to the L blow up. Okay, when everyone sends just elements. So for L equal to 1, this is root k, and k to the power, no, root k to the power 3 over 2, and k. Okay, now we'll go to proving lower bounds and hopefully show that both of these can become thetas. Both these bounds are optimal. That's what I'm trying to show. Okay, so let's start with the centralized lower bound. And the way it works is this is one of the simplest proofs I know of. It goes like this. So what do we want to show? We want to show that it's hard to, unless you have root k over epsilon square samples, you cannot tell the uniform distribution from the distribution that are far. So, so the way this proof goes is so let's design a large class of distributions, exactly 2 to the power k over 2 of them, that are defined as follows. So you are given a z, which is a plus minus 1 vector of length k over 2. Okay, so let z be a plus minus 1 vector of length k over 2, and what you are going to do is make small perturbations around the uniform distribution. So the probability of 1 is going to be 1 plus z1 times epsilon over k. And the probability of 2 is going to be 1 minus z1 epsilon over k. So you take the uniform distribution. Now look at the first two symbols. You make probability of 1 a little higher and probability of 2 a little lower, or the other way around, depending on the z. Okay? So now this way you are able to generate 2 to the power k over 2 distributions, one for each z. Okay? So now from the uniform distribution you make tiny perturbations. Okay, the first two symbols go up, down, down, up, and so on. And after you get this set of 2 to the power k over 2 distributions, what the way the lower bound works, and again I added this slide because some of you may not have the background on how this method or how these proofs go. So suppose someone can solve the testing problem, then we will show that they can solve another problem, and we'll derive a lower bound for this other problem. So suppose we first generate y, which is 0 or 1 with equal probability. If y is 1, then we assume that the distribution is just a uniform distribution. Okay? If y is 0, then we are going to first pick one of these 2 to the power k over 2 distributions at random, and then all the xi's will be generated from this distribution p of z. Okay? So x1 to xn will be from this p of z that's generated at random. So each p of z or each x1 to n is going to be IID, okay, from this p of z. But the overall distribution that you obtain by doing this process is not IID. In other words, it's a mixture of 2 to the power k over 2 IID distributions. Any questions about this? So all we are saying is you generate a big selection of distributions, pick one of them and generate n samples from them. So this is a mixture of IID distributions. So now the xi's or the distribution here will not be independent. And the goal we say is look at this x1 to n, and looking at that, try to estimate y. And if you are able to guess y correctly, you'll be able to say whether the distribution was uniform or far from uniform. So this is one hard instance for which they come up with a lower bound. So why is this easy? So now what happens is you have just two distributions here. You know x1 to n is uniform. You know this is a mixture distribution. Now you try to show that unless n is big enough, I can't tell these two distributions apart. And if I can't tell these two distributions apart, I cannot distinguish whether it's uniform or it's not. Okay, so that's the question. Tell uniform k x1 to xn, which is the uniform distribution, from this qz x1 to xn. Tell these two apart. And what Paninsky showed is that the L1 distribution distance between these two distributions over the n length samples is at most this something. And this right hand side will go to 0 unless n is more than root k over epsilon square. So you just try to make sure that the exponent is more than a constant. To do that, n has to be at least root k over epsilon square. And that's how the lower bound is proved. Okay? So the public coin lower bound that we prove is, we just consider the same set of distributions as the Paninsky construction. So we take this same set of to the power k over 2 distributions, and the xi's are generated by picking a single one of these distributions, so they are still IID. But now there are these messages that need to be sent which are not very long. Okay? So it's the same construction. The hard instance is either each player gets a uniform distribution, samples from a uniform distribution, or it's one of these, or samples from one of these two to the power k over 2 distributions. Okay? After having that, now they can only send a few bits. Okay? And what we show is that now you look at the distribution of the messages according to the sample. So you look at the same distribution, now they will, now when the distribution is uniform, it's going to induce some distribution over the messages. So M1 through N are the messages sent by the players. So now depending on the samples, there is some distribution over these messages. Now what we are saying is that the distance between the messages induced by the uniform distribution from the distribution induced by this mixture of the 2 to the power k over 2 distributions we said is at most this. So the same thing as before, times 2 to the L divided by k. Okay? So yeah, when L is log k, this is 1, when L is 1, this is like 1 over k. And this actually gives us a lower bound now. So n will be more than k divided by square root of whatever we had for the public coin bounds. Okay? N has to be more than exactly that. Okay, any questions about this? And this general methodology will actually also transport over to other things like local differential privacy that we'll touch upon later. So now you could have other local information constraints. Okay, so I'll just try to give a very hand-wavy argument for the private coin lower bounds. Okay, so right now what we saw is that let's say L is just one bit with k over epsilon square players, you can solve the uniformity testing, and with public coins that's optimal. For private coins, the only thing we could show is this k to the 3 over 2 from simulate and infer. Is that the best that we can do with private coins? And in general, how do we prove lower bounds when there are only private coins? So consider L is 1. Okay? Then the Paninsky construction is not going to work. Okay? Because if we know, like everyone knows, that the distribution is either uniform or this set of things, then what each player is going to do is to just send an indicator of whether its sample is equal to the sample number, to symbol number 1. Okay? So each player using its 1 bit just tells you whether it has seen symbol 1 or not. And if the distribution is uniform, what's the probability of symbol 1? It's exactly 1 over k. If it's not uniform, then it's either 1 plus epsilon over k or 1 minus epsilon over k. Okay, those are the Paninsky probabilities that we just saw. So in one case it's 1 over k, in the other case it's 1 plus minus epsilon over k. And you can show that you can tell these two distributions apart with k over epsilon square players. Okay. So why is, yeah, so Polinsky construction will not give us anything because this is a private coin protocol. Everyone just tells whether xi is 1. This can beat Polinsky construction. Okay? So now we try to look at it from a different perspective. This think of as sort of a min-max versus max-min, or your strategy then my strategy, or my strategy then yours. So let's say we know, okay wait, why is this here? Oh yeah. Okay, yeah, this slide should be after that table. So okay, we proved this public coin, there is a theta here, now there is this O that we are trying to take care of. The private coin lower bound. Oh yeah, this is the lower bound. So, okay, if we know that each player is actually going to just send an indicator of whether its sample is 1 or not, what we can do is to just make sure that P of 1 is 1 over K and make the distribution away from uniform on the rest. That's the rough idea. So now imagine again, if L is just 1 bit, what does each player do? It essentially sends an indicator of whether the sample lies in some subset. Now the subset is fixed, that's why it's a private coin product. Okay, essentially, there could be some distribution, but that's what essentially they do. So each player essentially sends an indicator of some set Si. The previous slide we were looking at each Si is just the set containing 1, the symbol 1. Each person sent an indicator of 1. Otherwise, each player could send an indicator of some set Si. So what we try to do is to look at these sets as some vectors in k dimensions. And each player is going to send an indicator of some set. In other words, they are going to give you information in some particular angles. Okay? So for example, previously when you had sets of size 1, they are going to give you information along these coordinates. Otherwise, more generally, you will get these vectors, they will form some kind of matrix. And what you do is, what we see is each player is actually giving us information about one of these directions, about the set that it has. And the entire work goes into showing that we can design distributions that are far from uniform, that are able to avoid these directions in which you are getting information. So once your private coin protocol is fixed, there are some directions in which you are getting information. We'll show that it's possible to avoid those directions by constructing another set of distributions that are all far from uniform. Okay? That's the essence. So for example, previously I said, if everyone sends indicator of 1, I just make sure probability of 1 is 1 over k. Similarly, let's say if everyone sends indicator of some set of size k over 2 that's fixed, what we'll do is just to make sure that the probability of that particular set is 1/2. And we put everywhere else subject to that constraint.
But you know, indicator functions are maximally informative. I mean, I could have sent some complicated polynomial of
Yes. Actually, it just goes through. And in fact, one of the things you do get is that it's maximized.
yeah, it is.
What if you cannot find such a set which, like P out of K elements do not have the probability of like P over K? Which is you cannot find such a set. Like if it has C elements and the probability is not C over K.
Okay.
Does that mean that in this case you cannot use this mechanism to prove this?
If the property is not, if it has C elements and the property is not C over K, that's good for us, right? So if I'm sending sets of size C, I have to make sure that I lose information on those sets.
Oh, yeah.
So I make sure that if a bunch of people are sending indicator about the same set, what we try to make sure is add one constraint that says that the probability of this set has to be what it should be for the uniform distribution, and try to avoid that. And design another over distribution. So yes.
So the sets are random.
The sets are random but fixed for a private protocol.
Yeah.
Private protocol, the sets are fixed.
So does private, does the nature that's picking this distribution, does nature know the randomness? Like Private means hidden from nature or is hidden from the other players?
Which part? The way the sets are created?
So I mean, you described it as like an adversarial thing. We have nature picking a
Great.
space distribution.
So the one thing I should have said is that the formulation is min-max. In other words, if the distribution is epsilon away from uniform, no matter what the distribution is, you have to be correct with probability 0.9.
But in the min-max, where's the averaging over the randomness? Can the worst case distribution depend on the realization of the randomness?
Yes, because now it's private coins that is fixed. That's where we gain. So we show that no matter how you fix these randomness that are all private, so once these sets are in some sense fixed, even if not, they depend on your private randomness. In that case, we can beat it by then designing a set of distributions that are valid for you. Yeah, so that's what this does, and that's how we fill the table. So now we know the exact upper and lower bounds for the tasks of learning and testing uniform distributions, and we showed a gap between private and public coins, which is pretty significant here. And for learning, there is no gap. For testing, there is a gap. For other tasks, we don't know when public randomness helps, when it doesn't. That's a great kind of questions. So here, public randomness does help for testing. For learning, it doesn't. I have like 1 minute for this. How much time do I have?
50 minutes or?
Is it 1 hour? I just assume everywhere is 1 hour. So I try to finish 5 minutes sooner.
All right.
Okay. Yeah, this is just since the title of the talk was statistical inference under local information constraint, we will have to talk about at least one more local information constraint. And here the constraint is called local differential privacy. This appears a lot in this applications on privacy, where what you want is that the central referee should not know anything about, or should not know a lot about what are the samples that these individual players observe or have. Okay? So that is actually characterized in this equation that says that if I see some message M, the probability that M could have been generated from a symbol xi or xi prime, they are not too different. So if you send me a message, after looking at the message, I won't have too much information about what your sample is. And again, so we have this paper with Lemma and Cody, who is in the CS department now, has moved to Cornell Tech. So most of these results port over, including that for testing there is a gap in public versus private coins. Even in the case of local differential privacy, whether you have public coins or not matters. Now maybe if you ask Google, they will say, we don't care about public coins, but at least for us, for me at least, it's very interesting. Okay. So this is some of the work that we actually have already done, this decentralized signal detection under limited communication. So you have some signal that's being observed at various sensors. It's either a zero mean Gaussian, so there is no signal, or it has some mean and some noise. There's a lot of work in that, but we think still may have something interesting to say. Multiple samples per user. Until now, I just said each player has just one point. What happens if there are more than one? We don't know how to use all that information. There is like a whole gap there. Even for learning, we don't know if each player has multiple samples. What should they do if they can send only one player? No idea. Then you can ask about other properties or other inference tasks like estimate the entropy of the distribution or estimate something else. And in general, the model is this. You have samples at each player or more than one. They pass through some channel that has some constraints. So for example, the first one we said that the output is only L bits long. The second one is this W is differentially private. You can think of any channel. So each player observes some sample that goes through some channel and you see the output. How do you solve this inference tasks? Okay. Thank you.
Other questions?
Do you know in what sense your lower bounds change if you test an arbitrary distribution rather than just the uniform one?
That's a great question. So the reason we did uniformity is you can show a reduction from uniformity to everything else. So uniform is in some sense the hardest to test.
So in this protocol, you're assuming that there is free communication from the referee to the player.
In the shared randomness case, yes. You can reduce the randomness. So right now we are using about k bits. We're sending like n equal to 1, we are sending a subset of size k over 2. You can try to reduce that communication. You can get down to log k bits. We don't know anything below that.
Basically, yeah.
Question, just to follow up to the earlier one. So if I understand correctly, you're doing like min, average, max, right? Min over schemes, average over the randomness, then worst case ordinal distributions.
For which case? For private randomness
Yeah,
or?
private randomness.
For private randomness, yeah. So the schemes are fixed. Yeah, you will do min over the schemes.
And average over randomness and then max over the distribution.
So randomness is just private, so you can, yeah.
Does it make a difference if you do min, max, average?
What would that correspond to?
It's like nature has to pick the worst case distribution, or what it thinks is the worst case distribution, then you get to randomize.
Now, so here is everyone picks their randomness,
Yeah,
and then nature can decide on a
okay.
prior.
So I'm asking
label.
if nature has to play first and then you randomize. is
Then
it-
you can beat, yeah.
Then you can beat.
Not
If
for
you
that.
can-
I mean, that's a maths result. Like there exists a distribution for which you can't beat.
No. So if I understand correctly, if nature picks the prior first,
Mhm.
like a set of distributions, then, and everyone knows that, then you can essentially have a public coin
Sure,
equal
but
to
there
zero.
exists a distribution for which you can't beat, if that's a maths result. Like whichever distribution you exhibited for which it couldn't beat it.
Yeah, so but if the nature picks the distribution and everyone knows the prior,
But I thought the bad distribution here, I thought depended on the realization of the private randomness.
Oh,
yeah.
So I'm asking if nature has to pick
I
distribution
see.
first and then
And
the
then-
randomness then is averaged, then does it change that?
I think it will become like public coins.
Okay.
I don't know.
Okay. All right. Other questions?
From one prior to beat that everyone knows. Like the Paninsky case, everyone knows, then they will just send sets of size 1.
Yeah. Well, the scheme has to be fixed first, and then the distribution, and then you average over the randomness is the formulation I'm proposing.
If the scheme is fixed
First.
then there is randomness at each user.
No, okay. No, the scheme is fixed first, and then nature picks the distribution, and then you average over the randomness and you use it.
Oh, that will be fine. I think. That will still
Fine.
be like private.
Oh, okay.
Yeah. If the scheme is fixed, then we can pick a prior.
Okay.
And then no matter what happens.
Okay. All right, other questions? All right, good. Thank you.